Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have AAS Journal author Kirby Runyon with us today. Hey, Kirby.
Hi, Frank. How are you doing?
I am doing fantastic on this March 18th of 2022 as we do this shoot. And that is a very cool shirt.
Thank you. Yes, the SLS rocket just rolled out to Launch Pad 39B yesterday.
Yes.
For the wet dress rehearsal, and the solid rocket boosters had the NASA worm logo on the side. So I'm celebrating one step closer to the moon.
And we are, and I hope that wet test goes well.
Yes, indeed.
So where are you located at, Kirby?
I'm currently in Baltimore, Maryland. I work at the Johns Hopkins University Applied Physics Laboratory down in Laurel between DC and Baltimore. I'm a senior staff scientist there. Been there about 5 years, and having a lot of fun exploring the solar system from APL.
Very cool. It's March. Do we have little green buds coming out on the trees yet there on the east?
Yeah, I just went for a walk, and leaves are starting to come out. The daffodils are out. Today's our first real spring day. It's in the 70s, so it's a nice day here in Baltimore.
Nice. I'm in Phoenix, Arizona. We are definitely turning the corner towards spring, and I actually have a bunch of grapevines on my wall.
Oh, fun!
And all the grapevines now have their little green new leaves coming out. So it's very cool. So in about 4 months or so, I'll get some actual grapes. It's very good.
You have some wine.
I haven't quite figured that one out yet, but yeah, maybe in my future I'll figure out how to do that. So, very cool.
Well, shout out to LPI, who gave me this wonderful mug when I was an intern there.
That is so cool.
Lunar Planetary Institute. They do great work.
That's so dumb. I'm just so used to, you're used to, oh, I got to look closer, and you move forward, but it doesn't make the object any bigger.
Zoom.
Crazy. Kirby, what do you like to do for research?
So I'm a geomorphologist. I'm a planetary geomorphologist. I love looking at pictures of planetary surfaces and teasing out the geological clues, teasing out the geologic processes that gave rise to beautiful alien landscapes across the solar system. And I also do geomorphology and dynamical experiments in the lab, studying processes related to impact cratering, specifically ejecta emplacement. So I'm a remote sensing geologist and a laboratory person. So we have a catapult at APL that simulates the emplacement of crater ejecta curtains. And so we can load it up with sand and gravel and fling sand and gravel for laboratory geology experiments. And we actually did some of that on a parabolic flight recently to see how reduced gravity affects that. So that was fun.
What's the mass you put in that catapult? Are we talking grams or kilograms?
We are talking sub 10 kilograms, in the kilogram range. Okay. For the parabolic flight experiment, those are quite a bit smaller. And I can tell you it's 1 cup full of sand, which is 900 grams.
Very good. I'll have to remember that next time I do see them. Very cool. And that is going to bring us to this very awesome PSJ, open access, people, so you can go ahead and get it. Identifying impact melt from the Smythii Basin toward an improved chronology for lunar basin formation. And Kirby, take us away.
Yeah, first want to give a shout out to my co-authors, Lyle Nelson. Lyle is finishing up his PhD as we speak at Johns Hopkins University in the Department of Earth and Planetary Sciences. I was really glad to get Lyle on this project. We started this at the beginning of COVID, and Lyle could not gain access to his lab for pandemic reasons. And so this formed a really nice COVID project for him. What's cool is that this was his first foray into planetary science. He's a terrestrial geologic mapper and brings a wealth of experience of geologic mapping from the field. Mm-hmm. And I was really anxious to get my hands on his skill set to apply his field geology skills to remote sensing geology skills and try to get some more terrestrial planetary crossover. So I felt really lucky to get Lyle on this project, and good luck to him as he defends in a matter of months. And then also Dan Moriarty, who is at NASA Goddard, and Dan is a whiz with the Moon Mineralogy Mapper M-Cubed spectral data sets. And really, I am not a spectroscopist person or a composition person. I'm a geomorphologist, and Dan really brings brings the power with spectroscopy, having done his PhD with Carly Peters at Brown University. So, there's a long, proud academic lineage there of really hardcore spectroscopy. So applied to planetary science.
Very cool. Very nice.
Yeah. So those are just my authors, and it's been a privilege working with them on this. This paper is hopefully it's really the second in what is hopefully a long series of papers focusing on potential exploration zones, whether those are landing sites or not, on the moon. And I like to somewhat controversially state that the moon is my favorite planet. I'm a geologist, so the moon's a planet. Hopefully these papers that I'm starting can lead to places to land on the moon and or places to rove to on the moon. If you jump down to figure 9, actually, at the very end of the paper, we show where on the moon a future mission could accomplish the science goals that we'll talk about in a minute. And this is the central peak of Schubert C crater within Smythii Basin. So you could land either up in the central peak in the central portion of the crater and do a few traverses to where we have actually mapped outcrops of what probably contains impact melt from the Smythii forming event. Or you could also land down on the crater floor for landing site option 2 on the bottom there, and then rove upward to collect some samples. And we tried to keep the slopes underneath 25 degrees.
So these
on
white,
there. So
these white are potential drive paths.
Those are potential drive paths. The white lines are potential drive paths.
Mm-hmm. Cool.
And the idea would be to do in situ age determination of the rocks, or do sample return so we could find out the ages on Earth of those locations. But this would be potentially useful for NASA or another national space agency, or even the commercial players that are starting to land missions on the moon.
Right.
And there's even what one might call philanthropic missions from, say, the Breakthrough Initiative. If they wanted to fund a mission to the moon, this could be a possible location, a contender to address important questions in lunar science. So we can jump back up to the front of the paper now.
One question: the coloring here is the slope because it's in degrees?
Yes.
Got it.
Yes, the slope coloring is in degrees, and where there is no coloring, that's because it's steeper than 25 degrees, which is that's a practical slope limit. The angle of repose for granular media is like 33 degrees. So maybe you could go that steep, but for practical reasons, you want to keep it lower, probably even under 20 degrees. But if you do a dog leg, you can go steep if your rover doesn't tip over. Yeah. But yeah, that's the color scheme, is the slope.
Okay, thank you. Very nice.
Yeah.
Okay.
So the question, the big picture question we're getting after, and where these landing sites could hopefully tell us about, is what was the moon's early impactor flux like? And by early, I mean from the beginning of the moon, 4.5 billion years ago, up to about 3.5 billion years ago. So the first billion years of the moon's impact history. What were the statistics of large basin forming events? And then we want to extrapolate that to what it was likely like on early Earth with our larger gravity and larger surface area, because life got started on Earth somewhere between 3.5 and 4 billion years ago, and we don't know how that happens. And one of the keys to understanding how that happens is by understanding the environmental conditions on early Earth, as geochemistry was somehow turning into biochemistry, which we still don't know exactly how that happens. And I'm sure the answer is fascinating, and I can't wait to hopefully we discover that sometime in my lifetime. But this is an area where planetary geology can actually help tie into not just astrobiology, but also the origin of life on our own planet, on Terran biology. So if we can understand the early impactor environment on early Earth, then we can start to address more what it is that life had to contend with. Did large impacts help start life, creating geothermal crucibles where bugs could use the thermal gradients and the chemical gradients to get started? Or were these extinction level events, or were they some combination of both? Right. So, it's a fascinating question. I'm not a biologist, but this is an area where geologists can contribute to origins of life science. And the moon is the only place to do that. Sometimes in lunar science, we make the very bad joke that the moon is the Earth's attic. and all of the, the moon uniquely contains the geologic record at 1 AU from the sun from the first billion years. Earth's surface is quite young comparatively because of these pesky things called plate tectonics and water and life. And the geologic record is from prior to 3 billion years ago is extremely scarce and heavily metamorphosed and modified. And most of Earth's rocks are younger than 500 million years old, whereas most of the moon's rocks are older than 3 billion years old. And so the moon really does uniquely, of anywhere in the solar system or really the universe, contain that geologic record of what could have been going on the first billion years of Earth's surface as well. So that's really a lot of the big picture motivation. Now, the moon has, depending on how you count, about 42 basins larger than 200 kilometers in diameter. Those are the big ones. Okay. Those are larger than complex craters. They're larger than the craters that have that central uplift mountain in the middle with the terraced crater rims. Yeah. And these impact basins can either be, peak ring basins with a ring of mountains when they're fresh, like the famous Schrodinger Basin near the moon's south pole, or you even get peak ring basins where you have multiple rings, like the Oriental Basin on the moon's far western limb, kind of straddling the near side, far side boundary there. And so it's roughly 42 craters of that scale. And what we're interested in is, when did those large basins form? When did those large basins form? And then by extrapolation, when did correspondingly large basins on early Earth form as well? So very good. The thing we need to do is to collect samples that contain the melted rock, the impact melt from those large basin impacts. One of the tricky things with the Apollo samples is that a lot of the Apollo samples probably have ended up determining the age over and over and over again of the same basin, Imbrium. And so this led perhaps erroneously to the thought that all the large lunar basins formed between 3.8 and 4 billion years ago, because they kept getting that same age when they did the age determination of these samples. Well, maybe not. It turns out that provenance, where a rock came from, and having very precise knowledge of that is absolutely crucial to determining the geologic story. So how old the rock is when it crystallized from a melt, that's important, but it's not enough. You also got to know its geologic context. Where did it come from? So
very cool.
The trick is to find cooled impact melt from these large basins where we can tie it to its provenance, and where we can be reasonably sure that it's relatively uncontaminated from other impact events or other volcanic eruption events or other geologic processing. And so it turns out that certain isotopic dating techniques can withstand gentle shocks without being reset. Probably. There's been some great work done on Earth, led by people like Kelsey Young and Gordon Osinski, where they dated the central uplift in Mistastin crater in northern Labrador, Canada, where the ages in the central uplift did not tell the age of the cratering event, but the age of the country rock that the crater formed on.
There we go. Okay.
In other words, the age of the central uplift showed the same age as the surrounding country rock outside the crater, which, if that's the age you want to know, that's good. There are other places you can go to measure the impact melt if you want to know the formation age of that small crater. Well, small is a relative term. So taking that, extending that logic further, we think that generally the central uplifts of complex craters that superpose the larger basins that we're really interested in probably contain impact melt from those large basins, and that those isotopic systems have not been reset since the large basin formed, despite being in the central uplift of a superposing crater.
Okay, I'm with you.
So generally speaking, a lot of impact melt from large basins is probably preserved and is datable in the central uplifts of superposing craters.
Okay.
I think that's the best way to say that. So,
yep.
We've got 42 basins. 2 years ago, we also did the Chrysium Basin and found that Yerkes crater. That was what journal was that published in? sorry, it wasn't the Planetary Science Journal, which was just getting started. That probably when we published it. But we showed that in that paper, we showed that the central uplift of Yerkes crater is probably the place to go to determine the age of Chrysium. And in this paper, we picked another basin and kind of drew one out of the hat and picked Smythii Basin. Okay. There's 42 basins, and they pretty much all got to have this kind of analysis done to determine where you would go to determine the age of these basins.
Okay.
And so we picked Smythii. It's a relatively well-preserved peak ring basin on the far eastern limb of the near side of the moon, very, very close to the near side, far side boundary. And we started, hunting around at some of the different complex craters that superpose Smythii Basin. So I'm looking at figure 1 now. And our first guess was that Neper crater towards the northern end there. If you zoom in on upper left on Neper crater, our first guess was, hey, there's a large complex crater superposing Smythii. Maybe that would be a useful spot to go to. But there's further south in Mare Smythii, where there's Mare basalt floods that have filled in the central depression of the original Smythii Basin. And Frank, if you expand your mouse orbit a little wider, you can kind of get to the inner ring of Smythii. You can, if you cross your eyes, you can sort of see a topographic boundary there. You can see it easier in the topographic map to the right on figure 1. But there are various interpretations for the multiple peaks of Smythii Basin. We frequently use Oriental Basin as an analog for a lot of these basins, because Oriental is relatively young, probably like 3.5 billion years old, and it's relatively unmodified with superposing craters, and there's gorgeous flows of preserved impact melt at various places. And so you can see where the impact melt kind of splashed out of the rings, but was also still contained within the interior of the basin as well. So we frequently use Oriental as an analog to kind of inform where we should look in other peak ring basins that are less well preserved than Oriental. So Neper seemed like a reasonable place to start, but we also didn't want to ignore some of the smaller craters like Haldane and Schubert C and some of the other unlabeled superposing craters in that, kind of where that dotted line box is. There's a lot of craters there. There's one right below the D in Haldane that looks like it has a central peak. So a number of these craters could have been potential candidates. So what we wanted to do was to look at the geomorphology and also look at the composition of the area to determine where one of these superposing craters most likely could have lifted up impact melt from Smythii, from the Smythii forming event. And that's where Lyle and Dan really went to town on a lot of this. And if we scroll down to, let's see, I think figure 2, take a look there.
Figure 2.
Bring it up on my end as well. Yeah, so Dan put together this Kaguya, the Japanese orbiter Kaguya multiband imager to look at plagioclase abundance. Neper central peak very high in plagioclase. The Mare of Mare Smythii is unsurprisingly low in plagioclase, being very mafic. And we looked at a number of these complex craters here in figures 3, 4, and 5, and looked at the composition there. Figure 6 is shows the absorption wavelengths of the 1 and 2 micron bands, looking at different mafic mineral abundances there to just inform the area. And that informed a lot of the geologic mapping that, in my opinion, forms kind of the crux of this contribution down in figure 7.
Okay.
So
figure 7. Let's go figure 7.
Figure 7.
Ooh.
So Lyle Nelson, being this expert terrestrial field geologist, this was his first time only having access to remote sensing data, and so he was the graduate student. I was a staff scientist he was working with, not his advisor, but I had fun working with him on that. I hope he had fun working on this with me. This was his first time doing anything off Earth, and so I had him map the different geologic units within and immediately around Smythii Basin. We saw that there was a lot going on in Mare Marginis to the north, that's outside of Smythii, but it's pretty much filled with just Mare basalts that kind of floods over into Smythii. So that's really the only geologic unit we mapped outside of Smythii.
Okay.
And I should mention, we've got geologic maps of much of the moon and quick map that ASU runs for exploring the moon, has wonderful compilations of lunar geologic maps, but this is really at a scale that hasn't been done. We're really zooming in on some pretty small areas on the moon and doing geologic mapping in detail that has not been done for the whole moon.
Cool.
So we felt that this was a worthwhile contribution. There's a number of lunar swirls, these high reflectance areas on the Mare where it looks like there could be remnant magnetism that has held off the solar wind. And so the regolith is less space weathered there. There's ejected material from Nepper. There's just basic Basin material in kind of this teal color throughout there. There's large superposing craters. We only mapped craters larger than 20 kilometers. If they were smaller than that, we didn't bother outlining them.
Okay.
But we really found that areas likely to contain impact melt actually probably aren't present in Nepper crater. So our initial hypothesis, we think, was untrue, but that Haldane and Schubert C crater probably do contain some uplifted impact melt. The nice thing about these impact craters is that they uplifted the floor of Smythii Basin, which was at one point an impact melt sea.
Yes.
And being an impact melt sea, of course, preserves the age of Smythii Basin. Again, these ages were probably not reset. At least all of the ages were probably not reset in the relatively small and fleeting shocks that go into the uplift of central peaks. And also it preserved the floor from getting flooded by this subsequent volcanism that probably happened over the last couple billion years after this formed. So, I think lunar volcanism more or less ceased roughly 2 to 2.5 billion years ago, but being lifted up above the lava flows, it preserved them from getting covered up in lava. I should mention, if you wanted to, you could probably drill through all this lava if you had a big enough lander. And if you wanted to do that, there's tons of impact melt from Smythii underneath the Mare basalt lava flows. But why go to all that effort if nature has done the work for you in lifting it up in central peaks?
Very cool.
So then simply using, maybe not simply, I don't know. This is science. It's not. This took a long time, but yeah.
Introductory.
Yeah. So if you assume the geologic map, no, and then so this led us to be able to interpret a geologic cross section to really kind of in figure 8, to really see where we think to see where the impact melt is. Of course, this is not data. A geologic cross section is not data. It's an interpretation of data, and it's a non-unique solution.
Sure.
But based on the presence of central peaks, we're able to infer what is underneath the Mare basalt lava flows. We're able to see what's beneath the ejected deposits from multiple overlapping cratering events. We can see where there may be faulting going on. And this helps inform the geologic context so that if you got samples from Smythii, you could have some high level of confidence of where that sample came from, what its geologic history is, and when you get an age for it, what that age means. It's the age of what? And hopefully the age of Smythii Basin. And again, you probably get that from the outcrop of Smythii melt, shown there in bold. Yep, and based on the compositional and geomorphologic mapping there, if you go further to the north, which is to the right, in this cross section, it looks like Nepper crater, while a fascinating and beautiful complex crater, probably is not exposing much, if any, of the Smythii impact melt. Right. So that's fine. But if you wanted to address other questions in lunar science, like the lunar volcanism and the history of lunar volcanism and the evolution and the compositional evolution of lunar lavas, Nepper crater could be an interesting place to go, but that would be a different mission with different mission objectives. And then as we started with, we will end with the exploration concept, where, Schubert C crater is, not a, you don't hear about this crater very often. It's, not one of these oft talked about craters, which is fine, but maybe it should receive more attention if you want to determine the age of Smythii. Now, one thing we didn't put in the paper, but that I'll just kind of throw out there as a freebie, is that Smythii Basin is also really interesting for the number of floor fractured craters. You'll note in Figure 7 geologic map and in some of the images there's a lot of faulting going on in the floors of Schubert C and Haldane crater, mapped as dotted lines inside the crater. Go back down to Figure 7.
Yeah, here we go. Okay, here we go. I got it.
Yeah, and my colleague at APL, Lauren Joswiak, who's a lunar volcanologist, did much of her PhD mapping and determining the formation of floor fractured craters across the moon. And what's probably happening is that you've got this igneous intrusion that's pushing up on the floor of these craters, sometimes locally erupting. Sometimes you get these Mare basalt flows from those, but they uplift and extensively crack and fracture the floors of these craters. So Smythii Basin is also interesting, not just in terms of telling us when it formed and then putting the formation of large basins on the Earth and Moon in context, but also telling us about the history of lunar volcanism. So these science concepts, and this should have gone at the beginning as part of the rationale for doing this, but understanding the cratering history on the moon and also understanding the history of lunar volcanism are two very large science concepts written about in the famously called SCEM report, the Scientific Context for Exploration of the Moon, that came out in the late 2000s and was really done under the auspices of the Constellation program, which was then canceled. But most of what's in there is still highly relevant because we haven't landed. I mean, China has landed on the moon since then, but no one else has successfully. Right. And so the Scientific Context for Exploration of the Moon, the SCEM report, is still a highly relevant document and a good read to informing the big picture science questions that we ought to be pursuing everywhere across the face of the moon. And so again, this impact cratering history and the history of lunar volcanism, I think, are fascinating topics worthy of lots of exploration, regardless of who's paying for it. So that's the status of this current research. I was very happy to have this paper accepted and published in the Planetary Science Journal. And it'd be gratifying if somebody decided to go there someday, based on, in part, maybe on some of our work. So there's still a lot more work to do. We've done 2 out of the 42 basins, and so there's 40 more to go. Yeah, so there's a lot more work left to do. And if somebody from NASA's Science Mission Directorate, the Planetary Science Division, is listening, I've got a lunar data analysis proposal in the system. So proposing to do more of this work. So, hopefully it doesn't have to be me, but if someone got to do this work, we've got 40 more basins to figure out where we should go to figure out how old they are. So that's kind of the next steps. And I'm happy to at least empower more of that. Maybe someone watching this can be inspired to take this on for a PhD project or something, and that'd be wonderful.
Very cool. Kirby, thank you so much for walking us through your very lovely article.
My pleasure, Frank.
Yeah, and you touched it a little bit there. I mean, you've only done 2. There's 40 more to go. Yep. But alternatively, are there other avenues that could offer some insights as opposed to the analysis you're doing? Is there additional, for example, we were talking about catapults and stuff. Yeah. So it's laboratory astrophysics that can be done. Is there theoretical calculations of kinetic impacts on realistic rocks viable? So, are there avenues, let's say over the next 2 to 5 years, to have those things make a contribution?
Yeah, I think there are more avenues of work to do. One thing that is related to this, and that my colleague David Kring at LPI, the Lunar Planetary Institute, has been pushing, is for a mission to Schrodinger Basin, because Schrodinger Basin is one of the youngest peak ring basins, but it superposes the South Pole Aitken Basin, which is probably like 4.3, 4.4 billion years old or so. And so you could basically bookend, you could bracket the age of large basin formation. That would help with this question. What the work I'm proposing to do would help say, okay, if we knew, even if we had that mission to Schrodinger and we knew the beginning and the end, we'd still want to know what the statistics are in between. Was it how stochastic was it? How smooth was it? Like a smooth decline?
Right.
What was the statistics of cratering and large basin formation during that time? So,
Right.
but a mission to Schrodinger Basin would still be a very important mission if it's focused on determining the ages of different lithologies. People want to go to Schrodinger Basin for other reasons. I don't want to have a mission go to Schrodinger that does something else and then have it be ticked off people's mental boxes and then not go to Schrodinger again to do age determination for different lithologies because quote unquote, we've been to Schrodinger. No, I mean, these are science goals. These are science driven, not location driven necessarily.
Right.
Other things. Yes. I'm glad you mentioned laboratory geology or laboratory astrophysics. As I touched on earlier, I have other research focusing on the mechanics of the emplacement of ejecta from impact craters. And that uses the facility called the Ejecta Catapult in the Planetary Impact Lab at APL. And it's basically a giant human-sized mousetrap that's a catapult that flings sheets of sand or gravel or other ejecta simulant onto different target surfaces, which could be sand or gravel, or in some cases, volcanic pumice, or even just a hard surface like plywood, which would represent a non-erodible planetary surface.
There you go. Does that catapult? Those are all sub-sound speed?
Yes. This is all like 20 meters per second or slower. Yeah. This assumes that you formed a crater. This assumes a crater formed, and then this simulates the ejecta emplacement without having to first create a crater.
Yeah.
And we are able to simulate kilograms to tens of kilograms worth of ejecta versus the small grams amount of ejecta that you get from hypervelocity cratering experiments, like you would get at, say, the Ames vertical gun range or our own hypervelocity gun at APL. So, this doesn't study cratering per se. It assumes the crater and then studies the results of the ejecta emplacement. So, there are experiments that could be done looking at the emplacement of both molten and unmolten ejecta. So, impact melt makes up a significant fraction of ejecta from cratering. And so one could imagine experiments, and we haven't done these, but let me just throw this out there. If, say, like molten wax mixed with pea gravel, and see what kind of mixtures and flowing you get to determine where stuff flows, and see if we can reproduce geomorphologies that we see on planetary surfaces. And we've already, using the catapult, simulated morphologies that we do see on planetary surfaces. So we have some confidence that we're not just throwing sand around in a garage. It's not really a garage. It's kind of like a garage. So,
that could be fun too.
that it's actually simulating something geologically real.
Very nice. Well, I certainly look forward to some of these experiments and seeing the other 40 odd craters that remain to be done. And so good luck with your proposal. Hello, panel review, if you're listening. And that will do. And so Kirby, thank you once again. And everyone, I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Thanks. Bye.